Okay, so now let's talk about the dependent samples t-test, right? This is different from the independent samples t-test, as the name would suggest. So let's talk about it. First of all, just a little bit of concept review before we get too deep into it, right? So a little bit z-tests and t-tests, right? These are about trying to identify how much difference is enough to say two things are different, right? So two samples are different, or a sample is different from a population. And this is all based on probability, right? If things are different enough, there is a low probability that they are the same. And then if there's a low probability that they're the same, then we say, okay, we conclude that they are in fact different. So if we're doing a single value in a population, where we can use a z-score, right? Where z is the difference between the particular value or the mean of my sample compared to a mean population mean divided by the population standard deviation, right? That gives us a z-score. And if that z-score is too far from zero, right? So 1, 2, 3 standard deviations away, we start to say there's a low probability that these things are the same. Then we can look at sample and a population, where again, we can divide, we can compare the sample mean to the population mean. We divide it by the standard error that is based on our sample size, right? Or we can use the t-distribution because we often don't know the population standard deviation and we rely on the sample standard deviation. But again, here we're using t just gives us the difference between our sample mean and the population mean divided by the standard error and our estimate of the standard error based on t. And then we did independent samples t-test, right? So instead of knowing anything about the population, we just have two samples, a sample that is from what we presume to be a particular population, a sample from what we presume to be a different population, and we are testing to see if they are in fact from different populations, if they are so different that we can say they are not the same. The samples are made up of different people that are not related really in any way, except that they happen to be participants in our research. Examples of this are a treatment group and a control group in an experiment, right? Where the control group represents maybe the population writ large, and our treatment group represents the population of people who have received the treatment. And so we're trying to see that the treatment, whatever it was, whether it was a training, whether it was a drug trial, whatever it is, we're trying to see if the treatment created a different population, if the result is they're so different, right? And so we have, so that's one way to look at it. It might just be sets of people who are different on certain characteristics, right? So they work in different bank branches, or we're comparing people who are high in conscientiousness to people who are low in conscientiousness, and we're seeing if they're from different populations on some other variable. Again, the difference here is that we compare the difference of the means of our two samples and divide it by some standard error, right? And here, the pooled standard error, where it's where we pool these two sets, the standard error based on these two sets. So, and again, we get t based on some degrees of freedom, and if that t is too extreme, if it's too big, then we say, okay, we're going to conclude that these samples are in fact from different populations. Let's turn, though, to dependent samples. So instead of independent samples, where we have different people in different groups, what changes if the two groups are, in fact, related in some way? So, for instance, if I do pre-test and post-test, right, pre-test group is related to the post-test group because of the same people, right? We're observing the same person and the same people under different conditions. So any particular participant is actually part of both of these groups. And so they are related in some way. They're no longer independent of one another. And this can be, so we use this in two ways. We can do these repeated measures where we have the same person twice, or if we move beyond t-test, we can do more than 2 times. Or also another way to look at it is matched samples or paired samples where we have some predetermined coupling, right? So instead of looking at one person twice, we might be looking at spouses, right? Spouses' answers to certain questions are going to be related to one another, right? So if we ask spouses about the quality of their marriage, then we would expect, the husband and wife, or husband and husband, or whatever that coupling is, we would expect that their answers would be related to one another in some way. And so we no longer have that independence of our two samples, that they're related in some way. And this is important because the idea of correlated error terms. Right. So in classical test theory, we have the idea that X, which is our score on any particular variable, is a sum of both the true score, right, so with the kind of big T truth, plus some error term. Error then accounting for all of the random stuff that contaminates our measures, right, that people bring to the table. Now, the independent samples t-test relies on the assumption that the error terms are unrelated to each other, that they're uncorrelated. But when we have dependent samples, when we have these paired samples, either the same person measured multiple times or some coupling, some predetermined coupling where people are related, it turns out then that these errors are in fact correlated with one another. And so that brings us some advantages and disadvantages, but either way, we have to account for them in our tests. So there are some advantages to the dependent samples t-test. One of the huge advantages is it removes variance due to differences between people, right? So just intuitively, we understand that a pre-test and post-test setup gives us kind of some better information than just comparing two groups, one who got the treatment and one who didn't get the treatment, right? We're seeing actual change. So that's actually kind of cool, right? This helps us control for individual differences when we're doing our research. The other thing is dependent samples actually give us more power. So for the same difference that we might see, we need a smaller sample size because additional variance is being accounted for by using the same people over and over again, or by using these matched couplings. So for the same sample size, the t value itself will be more extreme for the same effect size, right? So given the same sample size and the same effect size, if we're using a dependent samples t-test, the t will be more extreme, which makes it more sensitive. It makes it easier to detect those differences than if we use the independent samples t-test. Now, there are some disadvantages here, right? So it turns out that the answers, the big T truth, are also affected by each other, right? So even if we're looking at one person measured multiple times, the second answer is going to be affected in some way by the first answer. So there's a loss of motivation, or maybe pre-test, post-test, where we just remember what we did on the first test. We've had the practice effect of having done the test once already. Some of that is going to get pulled into it. So that is a disadvantage and one we should keep in mind. And there are lots of advantages as well.